Now we're going to make some isomers and assess their polarities. Okay, on this one, so you're going to start with 2 carbons bonded together, and you're going to find when you do this that when you make the skeleton, there's more than one way to make it, as far as more than one way that it would make sense for it to be connected. One way would be to put the fluorines on different carbons. And by the way, when you finish this structure, we do have some lone pairs around these, but other than that, there are no lone pairs. That is a complete structure. The other way is, what if we put both of the fluorines on the same carbon? This is what we mean by 2 molecules that have all the same atoms, but they're connected differently. They're connected in a different order. This one has a fluorine on each carbon, and so we call this a 1,2 isomer, and we may even say difluoro. We don't have you name them. You don't have to name them, but sometimes naming them helps you kind of understand the differences. So this is what I mean. I'm saying the locations of those fluorines. This one, we would call it, we would number from this end, some organic chemistry nomenclature. We would call this a 1,1 difluoro. But anyway, so you can tell that they're different. And you might be wondering, well, why don't we, these are the only 2 isomers, only 2 ways to draw it, but, or only 2 ways they can be connected. And you may be wondering, well, what about if we had put this fluorine up instead of down like this? And the thing is, it's really the same. It's the same thing. In other words, these 2 are actually the same compound. They're both the 1,1. And if you look at the way we named them, we would come up with that. So let's think about why they're the same. And the thing is, you have to think about the geometry in 3 dimensions. And so I'm going to draw this carbon. And those lines are, I'm not going to draw the rest of the molecule. These lines are on the screen. Okay, but to make the tetrahedral shape, because that's tetrahedral with 4 electron groups and 4 atoms, so to make the tetrahedral shape, I need to make this look 3D. And the way organic chemists do that is by putting a dashed line for something that's pointed behind the screen and a wedged line for something that's pointing out toward you. Okay, so these 3 atoms are forming that triangular base of a tetrahedron, and this is kind of the one we would say is straight up. So if you can kind of imagine that in 3D. Well, the thing is, this bond, single bonds rotate. So if this bond twists, then these 3 will essentially just switch positions. So they would just be able to twist. And so what we'll say about that is that those 3 positions are equivalent. Those single bonds rotate, and they are constantly rotating. So what I mean by that, that they're equivalent, it's that when I draw these, it doesn't matter where I put the 2 fluorines and the hydrogen, those positions are always twisting and in the different places as well. So that's why these 2 are the same molecule. It's just a matter of the twisting of that end. Okay, so we have two isomers, and that's what they are. Let's look at them and decide about their polarity. So I'm going to redraw our two isomers and kind of in the 3D way, because you have to look at the shape to decide the polarity. And just to keep things simple, I'm not going to draw all the lone pairs, just to make it a little bit less messy. You should, when you draw the dot structure like these up here, you should, but on this structure I'm not going to. Okay, so where's the polar bond here? On this one, the polar bond is the carbon to fluorine bond. Okay, but if you can imagine, this bond is rotating all the time. So the polarity from this one is actually kind of straight out this way. And then the same thing on this one. If these positions are constantly switching because this is twisting, then the polarity caused by this fluorine is actually a net straight out this way. And so overall, we're going to expect this to be a nonpolar molecule. The other one, by the way, saying something as polar or nonpolar is really kind of can be a gray area. Not very many things are perfectly nonpolar. So just so you know, but definitely more nonpolar than this one's going to be. Let's draw this one. So on this one we have the fluorines on the same carbon. And so it doesn't matter that this is twisting, these fluorines are on the same end and they have a net pull for electrons. This carbon is going to have its electrons really pulled out that way. So the net pull of these, even if they're rotating, is going to be out this way. So this one is a polar molecule. Okay, another little summary I wanted to give you was that as far as what makes a bond polar or nonpolar. So anytime you have, let's just make a little heading here. Bonds. Okay, anytime you have the same element on either side of a bond, that's going to be nonpolar. And so in these molecules, the C to C bond in the center is nonpolar. And then carbon to hydrogen is a very, very common bond in organic chemistry. So it's good to know that that bond is definitely nonpolar. Considered nonpolar, I should say. It's not perfectly. And then carbon to fluorine is a very polar bond. It's very polar because fluorine is very electronegative. Remember, electronegativity increases as you move to the right and up on the periodic table. And fluorine is right up there. It's the most electronegative because we don't say that about the noble gases. But anyway, that's how we assess these two isomers.